Okay, so here's 2.3. This is question 8. After this, we'll do question 7. Use cylindrical shells to find the volume of the solid generated by rotating this curve about the x-axis, and we're given some bounds for x. Okay, so what I want to do to begin with here is to give a little bit of an idea for how to set up these things. When we're working with volumes, it's a three-dimensional object, and those can be hard to get a hold of, right? Can be very difficult to graph. The key with these solids of revolution is that you don't really need to know what the 3D object looks like in order to find its volume. Like, that's kind of the idea, right? We have this 3D object. But if I'm looking at a problem like this, I can just look at the two-dimensional thing, and that's enough for all of the setup stuff that I need. Okay, so let's go ahead and take a look. So let me just draw quickly a graph of y equals 7 ln of x, right? That's the natural log function stretched out a little bit. Okay, my x values are going to be between 1 and e. I know that at 1, that's where natural log is 0. And up here at e, ln of e is 1, so that's going to be at 7. Okay, so the part of this curve that I care about is this piece in here. Okay, and then we're rotating the curve about the x-axis. Change that color here. About the x-axis. Okay. One of the ways that I like to think about how to do problems like this. Before we get into doing this one, what I want to do is maybe really quickly just go over the difference between using the method of cylindrical shells, which it says to use in this problem, and the method of discs and washers. So I'm just going to pull up our book really quickly. Just so that we can see a difference in setups a little bit. Okay, so here they talk about solid of revolution, right? You get some curve, and you rotate it around the axis, you're going to get a round-looking curve, or a round-looking solid. Okay, now in the book and in the notes, we talk about the disk method and we talk about the washer method. Those are really the same methods. The disk method is just the simpler method when I'm using the, I'm rotating about like the x-axis and I get a solid. And sometimes we have the same thing called the washer method. And that's just where you have a hole on the inside where your axis of rotation is, where the region is not like butting right up against the axis of rotation. Okay. Both of these methods are otherwise the same idea. And if I were to look at the piece of the curve that I'm taking the area under, if I was thinking about this as an area problem, I would want to set this up with my rectangles going up, down, right? So remember when we were learning the area between two curves, we said, well, we can either integrate dx or dy, whichever one is more convenient. We want to still utilize those skills. So when I'm setting up a problem, I want to figure out, is it easier to integrate dx or dy, right, with my rectangles going up, down, or going sideways? And here, sideways wouldn't make sense at all, right? It would be a ridiculous mess. So I'd want to integrate going up and down. Okay, and then when I rotate, I also want to pay attention to which way I'm rotating. So if my rectangles are going up and down, when I rotate them, then I'm going to form a disk, so I'm using the disk method. Or if there's a gap there, right, my rectangles are going up, down, when I rotate, I'm going to get a washer. Okay. In section 2.3, we have the same idea. I have some area that I'm rotating. Get to to a different picture. Well, we'll look at this introduction one. The idea is that if my rectangle is going up, down, but I'm rotating about the y-axis, I don't get like the same shape. Or I guess, I mean, maybe technically it's a washer, but the idea is that it's really thin, you know, so it's kind of like this shell piece that we have. And so that's why we use the method of shells. So typically what we do in a problem, not in this problem because it tells us to use the method of shells, but typically what you do is you first determine, do I want my rectangles to go up, down, or left, right? And then I look at which way are we rotating, and that's going to determine what method that we use. Okay. And they summarize this, you know, in the book they have a little summary here, but you know, same idea. Okay. So when we look at our problem here, the way that I would want to set this up, I'm given y equals some function of x. That seems like, okay, I can set this up with my rectangles going up, down. When I rotate about the x-axis, that's going to give me disks. So this looks like it's really set up nicely for the disk method, but it tells me to use shells. So I say, okay, in order to get a shell out of this, I have to start with my rectangles going left, right. Okay. So what I'm going to do is I'm going to rewrite this equation. Right? I'm going to solve for x. So y over 7 equals ln of x, and I take e to the power of both sides. Okay. So now I have x as a function of y. And my y values are going to go from y equals 0 to y equals 7 instead of from x equals 1 to x equals e. All right. So then I need to figure out how to set this up then, and I think that it's probably a good idea to use you know, your reference materials, right? And so this, I'm just going to refer back to here because it's kind of all in one place here, right? Disk method, washer method, and shell method. Okay, so the way that I remember them is when I'm rotating a disk, right? I'm forming a circle. Okay, area of a circle is pi r squared, and I'm integrating that area as I go. For washer, it's the same idea, except I have to subtract out the inside circle because that's the whole. Okay, and for the shell method, when we create these shells, it's kind of like a cylinder, right? So my volume of a cylinder is, you know, 2 pi RH. So I have 2 pi, and then we have this y that is like the radius, and then the function values, the height. Okay. So it's you know, that's like a rough way of thinking about it without having to go through, you know, in the lecture videos and the notes, they go through that in detail, but that's just like my quick way of sort of thinking about it. So we're using the shell method here. Okay. All right. Now, one of the things that I want to be aware of, you know, difference here, well, yeah, this is rotating around the x-axis. If you rotate around the y-axis, you have to make, you have to account for that, right? So you'd be integrating these dx or dy in the shell method dx. But we are integrating around the x-axis, so everything lines up nicely. Okay. So I'm going to go ahead and write down my formula. The volume is the integral from a to b of 2 pi y times the, remember that the function here is g of y, right? And we're integrating dy. So I want this e to the y over 7. So we said our y values are going to go start at 0 and go up to 7. And I have e to the 1/7 y dy. Okay. It's a little bit annoying that they required you to use shells here, because this this gives us an integral problem that I don't think that you can solve yet. I think that you need integration by parts to do this. Maybe that's why you're running into trouble. Because I have a y here, and because I have e to a function of y, if I try a u substitution, I'm still going to end up with a function and my exponential. You're not going to be able to integrate this with just a straight u substitution.
Makes sense. Yeah. I was a little confused on after that part where to continue. So
I think I'm just going to pull this one out of the homework. I mean, I think we could probably solve this using shells, but we run into a little bit of a problem there too, because then we'll have the natural log function squared. The 2 doesn't come down there because it's not on the x. It's the whole log function that gets squared. So I think for now we'll just skip it. We'll come back and revisit it. We'll be doing integrals like this in the next chapter, but I think that maybe this was a misplaced problem. Okay.
So just skip this one, right? We don't have to do it.
Yeah, so we'll skip this one.
All right.
Okay. Problem 7 won't have the same issue. Problem 7 we'll be able to integrate. Okay, so this is again using shells. So I'm going to go ahead and set this up the same way. So here are our graphs: y equals x, and then we have y equals 10 minus x. Let me use the same color here. Okay, so we want to find the volume of the solid obtained by rotating the region bounded by these two graphs and the x-axis. So what I want to do is look for what region is contained in there. So I want the first green curve, the second green curve, and then the x-axis. So that's different color. It's too dark. So this is the region that I'm rotating. Okay, it says we're rotating it about the x-axis. Okay, so if I want to use shells, then I need to set up my rectangles going sideways so that when I rotate, they'll form a shell. Okay, so let's start by finding this intersection point. And it doesn't matter if I have these solve for x or solve for y when I find the intersection point, just whatever's easiest. So I'm just going to go ahead and set these two equal to each other. So x equals 10 minus x. So 2x equals 10, x equals 5. Okay. So this is the point 5 comma something. Because this line is y equals x, then if x is 5, y is also 5. Okay. So if I'm rotating using shells, let's go ahead and write down our formula. Volume is the integral from a to b of 2 pi y g of y dy. My a and b, these are y values. Okay, so I want to start at a y value of 0 and end at this y value of 5. So we're going to integrate from 0 to 5. And my function is going to be how tall, or in this case, I guess, how wide this rectangle is. Okay, so that's the difference between my two functions. Okay? So I'm going to take the function on the right, 10 minus x, and subtract the function on the left oh, I'm sorry, I wrote 10 minus x. I want these as functions of y. Okay. So this width is g of y. So g of y is, if I solve this first one for x, if I add x and subtract y, I'll get x equals 10 minus y. And this one's already solved for x. X equals y, right? So y equals x, same thing. Okay, so I'm going to take the one on the right, 10 minus y, and subtract the one on the left, which is just y. So I get 10 minus y, or 10 minus 2y. Okay. So before we integrate, I want to make this look nice. What I'm going to do is take this 2 pi y and distribute it so that I don't have a multiplication anymore. So 2 pi y times 10 is 20 pi y. 2 pi y times negative 2y is minus 4 pi y squared. And I'm still integrating dy. Now I'm ready to integrate using the power rule. The 20 pi is a constant, it hangs out. I integrate y, I get 1/2 y squared. Okay, the 4 pi hangs out. When I integrate y cubed, we get 1/3. I'm sorry, when I integrate y squared, I get 1/3 y cubed. Okay. And then I can go ahead and plug in. I'm going to do a little bit of algebra cleanup just to make this look a little bit nicer. 20 times 1/2 is 10 pi. So I can, well, let's write it. So I have 10 pi times 5 squared minus 4/3 pi times 5 cubed. And then I subtract this whole thing with 0 plugged in. Well, when I plug in 0 for y, I'll just get 0 because it's polynomial. Okay. And then we get our answer from there, right? You can clean that up. I guess here we're going to write down a decimal anyway. All right, does that make sense?
Yeah, thank you.
Okay. All right, another homework question you guys want to go through? I know some people had emailed me about that window problem from 2.1. So at some point I want to go over that, but I want to prioritize what questions you guys have first. Question 6 from 2.3. All right, here's question 6. Use cylindrical shells to find the volume of the solid obtained by rotating the region bounded on the right by the graph of g of y equals 7 root y, and on the left by the y-axis for y between 0 and 6, rotating about the x-axis. All right. So it's not strictly necessary, but I like to just draw a quick graph just so I can keep all this information straight. Okay. So g of y equals 7 root y. We have to be a little bit careful of graphing that. What we're doing is when you input y, you're outputting an x. So this is x equals 7 root y. Okay. If I wanted to graph that, it might be easier to think of this as 1/7 x equals root y. So x squared over 49 equals y when I square both sides. So if y equals, x squared over 49, that's going to look like a parabola. Okay, the difference is if I write x equals 7 root y, the square root of y is always going to output a positive number. So I don't actually have this left side of the graph. Okay. So the region is bounded on the right by this curve. It's bounded on the left by the x-axis. And we're told that y is going to vary between 0 and 6. So if y is allowed to vary between 0 and 6, then the region that we have bounded by all of these is in here. Right? And again, we're not really given the choice. It says to use cylindrical shells, so I want to set up my rectangles going left, right. Okay, but that's kind of already neatly set up for us because we already have, you know, our g of y, right? We have our function of y. So we're ready to set this up. So volume is the integral of 2 pi y g of y dy. Now we have to be a little bit careful. The g of y I'm using here doesn't have to line up with the g of y that we're given in the problem. It does in this case because I'm going between the function and the axis. But if I was going between two functions or something like that, the g of y we put in here is how wide our rectangle is. Okay, we've got to be a little bit careful about that. But in this case, we're all right. So my y values are going from 0 to 6. Oops. 6 got a little messy. Okay, so we have 2 pi y times 7 root y dy. To integrate this, I need to get rid of the multiplication. I can't have the variable multiplied by, you know, another function, so I've got to combine these together. If I think of root y as a y to the 1/2, when I take y to the 1/2 times y, I'll get y to the 3/2. If you like, you can factor the constants out. Not really necessary, but oops. Instead of writing it as a 2 pi times 7, I'm just going to write that as a 14 pi. So then we have y to the 3/2 dy. And now this we can integrate. Right? I add 1 to the power. Divide by 5/2 is the same as multiplying by 2/5. Okay. So we have 28 pi over 5 times 6 to the 5/2 minus 28 pi over 5 times 0. Okay, and so then that's our answer. All right, does that make sense?
Yeah, thank you.
Okay, another question. 2.2, number 10. All right, here's 2.2, problem 10. The graph above shows the base of an object, right? So this is the bottom. We want to compute the exact value of the volume. Cross sections, which are perpendicular to the base and parallel to the y-axis, are equilateral triangles. So let me try and draw what this looks like in its third dimension. We're given the two-dimension, okay? And the idea is that we can take like slices this way. And if I took a slice this way, this is the base of the object. And these slices are, in this case, equilateral triangles. So this would come up out of the page as a triangle. Okay. So down here where there's a point, there's no base. So this would just be, a point. And then I'd have a triangle going up and bigger triangle, and the slice would be a much bigger triangle, right? And the slices at the very end would be this gigantic triangle, right? Coming up out of the page, right? So this would be kind of sloping up and then straight back. All right, again, we don't really need to know what it looks like in 3 dimensions in order to find its volume. We're going to use the method of volume by slicing, and what that says is that the volume is the integral from A to B of the area of the object. Okay, so what I need to do is say what is the area of these slices. Okay, so A of X is the area of the slice. All right, now the slices are equilateral triangles. So if I have an equilateral triangle where it has a side that we'll call, say, S, I need to be able to find the area of the triangle. Okay, it's probably easiest just to look up area of an equilateral triangle. If you want to be real mathy and say like, oh, how do you find area of an equilateral triangle? You could always just break it up. Now it's equilateral, so these left and right sides should be exactly the same. Okay. So then this would be S, and this would be half of S. Okay. And so then what I really want to do is find the height, because I can find the area of any triangle if I know, the base and the height. Okay. So that's one way to do it. I can use the Pythagorean theorem to find the height. So h squared plus half of S squared equals S squared. So if I subtract 1/4 S squared from both sides, I'll get 3/4 S squared. And then when I take the square root, I'll get that the height is √3/2 times S. Okay. So then my area is √3/2 S, that's the height, times the base, times 1/2. Okay. Now another way to find area of a triangle, I'm just gonna go off here on a little bit of a trigonometry rant. Okay. So it's equilateral, so this is a 60-degree angle. Okay. And the sides are S, and you can find the area of a triangle. Well, you know what? Let's not go too crazy, but you can just use a trig function instead, right? And trigonometry you probably learned at some point and maybe forgot the area of a triangle that's not where you don't have the height, where you just have the sides. Okay. And you can do that with the sine function, but okay, we already have the area, so let's not get confused. All right. So this is the area function that I want, right? The area of one slice is √3/4 times S squared, but that's a little unsatisfying because I need to know what this is as a function of X. Okay. And since the base of my slice here, well, it's going to change. It depends as I go from 0 to 2, it's getting bigger, and then from 2 up to 6, those slices are staying the same size. Okay, so I'm going to split this into 2 parts. What I'd like to do is find an equation for this line here. Okay, so this line goes through 0, 0, and this line goes through 2, 6. Okay, so I can find the slope of that line, change in y over change in x, which is 6 halves or 3, and it goes through the origin, so just y equals 3x. Okay, so this y height here is 3x, and the side is going to be double that. So that side of our triangle is 2 times my y value, which is 2 times 3x, or 6x. Okay, so at least between 0 and 2, this gives me a function for what S is, and I can plug that in. So area now as a function of x is root 3 over 4 times 6x squared. Okay. And I'm going to simplify this a little bit. 36 divided by 4, we can simplify down. Right, so we have 9 root 3x squared. So now our volume is going to be the integral from 0 to 2 of my area function, 9 root 3x squared. Okay, or at least that's the volume of this first part, right, where it's getting bigger. And then I have to add in the piece where we go from 2 to 6. From 2 to 6, the length of the side isn't changing at all, right? That base is always the same. So I don't really need an integral, but I'm just going to use it anyway because we don't want to get confused by changing things up halfway through the problem. So I think it's probably easiest just to continue on. Okay, but here the length of a side is just, well, it goes up by 6 and down by 6, so a side is just 12. Okay, so on this piece, if a side is 12, then the area is root 3 over 4 times 12 squared. Okay. All right, so now I can integrate away. This first integral, the 9 root 3, hangs out. When I integrate x squared, I get 1/3 x cubed, going from 0 to 2. And 9 times a third will give me 3. So then we have 2 cubed minus 0 cubed. 2 cubed is 8. 8 times 3 is 24. Okay, the other side is actually really easy. I have 12 squared, right, which is, 144. And then, I can divide that by 4, but all of this is a big constant, okay? So that's just going to hang out. And so I'm really just integrating a constant. So I'm going to get that constant times x. Okay. So then if I take that 144 and divide it by 4, what do we get, like 6? Not 6, 36. Wait a minute. Don't do math in your head. I'm so confused. Yeah, 36. Okay. So we have 36 root 3. And then when I plug in for x, I'll have 6 minus 2, which is just 4. So I'm back to the 144. Okay. Does that make sense? I feel like I started that going in a lot of detail, and then I kind of sped up as I went. So, do I need to go back and give some detail there? Okay. All right. Another question you want to take a look at? Okay. One of them that I wanted to go through, because I know that some people had asked me about that, so even if they can't make it right now, I want them to be able to see this when we post it up later. Out of 2.1 was this window problem. That to be fair, I think is a challenging problem, so I think it's worth going through. So let's go ahead and take a look at it. Now, one of the things that I think is helpful about this problem is that they give you some of the setup ahead of time. Okay, so normally if you just see something like this, you get to make choices for where you want your x and y axis to be, And there's more than one reasonable choice, right? You could say, I might want the center of the circle to be my origin. That makes the equation of the circle really nice. In this case, though, they say you use this solid line as the y-axis and the dotted as the x, so the origin is going to be here. So this is the point 0, 0. And that makes the circle a little bit, the equation for the circle a little bit more complicated, but I think that it helps the parabola a lot, and the parabola is the harder part. So it's actually a nice trade-off where you make the hardest part of the problem a little bit easier. Okay, find the distance from the x-axis to the top of the circle. Okay, so that's the first thing that they're asking us. And if we had the equation for the circle, that would be nice. That would be easy. But we don't have that yet. Okay, so we say, well, you don't have to do the parts in order, but you know, I think in this case the reason that they're asking in this order is because that's actually going to be, you know, a useful way to go. So we're just going to follow the directions that they give us. Okay, so how do I go about finding that distance? Well, one of the things I can do is you know, take advantage of the information that I know, right? So I can figure out these points. If the top of the parabola is, you know, it's this dotted line, I can see that it's nice and symmetric. Same with the circle, nice and symmetric. So these points are going to be symmetric. And if they're 11.8 feet apart, then it's going to be half of that in either direction, right? So if I look at how wide this is, I just take the 11.8 and cut it in half. And I think that's 5.9. Okay, so this is the point 5.9 comma 0. And this one will be negative 5.9 comma 0. Okay, while we're labeling points, we'll just go ahead and label that top point. This is 6.65 feet up, and it's on the y-axis. So this is 0 comma 6.65. Okay, so that gives us some points to work with. Now, what we need to do is know something about this circle in order to figure out how high it is here, right? How far, you know, and that's going to tell us how far down the circle drops. So that's really going to be able to give us the equation of the circle. So I guess there's more than one way to go about it, but let's go with the easiest way. Let's see. I don't know. I feel like just finding the equation of the circle is probably the easiest way for me. So then I would find that equation first and then find the distance. And for some reason, I'm blanking on how to do it backwards. Does anyone want to throw out an idea for how to do it backwards? How to find that distance first and then the equation? All right. Well, if nobody wants to do that, let's write the equation of the circle first, and then that distance is nice and easy. So typically, equation of a circle if it's centered at the origin, it looks like x squared plus y squared equals r squared. Okay, and I know the radius, so that's really nice. When it's not centered at the origin, what we do is we just say, okay, I'm going to shift it. And the way that we shift it is you shift left, right by adding something onto the x, and you shift up and down by adding something onto the y. This hasn't been shifted left and right from the origin, so the x we leave alone. We're just going to add something to the y. So for our circle, this is going to be x squared, and then I'm going to take that y and add something to it, right? So like a y plus, maybe we call it an h squared equals r squared. And I know what the r is, right? Because we're given the radius is 13.6. Okay, so now what we can do if I want to find out what this unknown constant h is if I just plug a number in for x and y, and I have this point, 5.9 comma 0. So when I plug in for x, 5.9 squared, and I plug in y as 0, now I just have one variable, and I can just solve it, right? And I can isolate it, right? So 0 plus h is h squared is h squared. And then I have 13.6 squared minus 5.9 squared. And I'm just going to go ahead and punch those into my calculator and get a decimal. So I get 150.15. So I take the square root of that to figure out what h is. So I'm going to round it a little bit, although if I use this computation, I'm going to use all of the decimals in my calculator. But this is about 12.25357. Okay. So then that gives me the equation for my circle, right? Because now I have that h, right? So the equation of my circle is going to be x squared plus y. And remember when we're shifting, when I'm plugging on the inside here, y minus h is for an upshift, so the plus goes down. It's kind of backwards because it's inside the function. So we do indeed want the plus 12.25357. Squared equals 13.6 squared, which is 184.96. Okay, so then if I want to know the distance between the origin and this point, the distance from the x-axis to the top of the circle, that's just the y value when x is 0. Okay, so I can just take my equation of a circle and plug in 0 for x. So when x equals 0, then I get y plus 12.25357 squared equals 13.6 squared. I square root both sides and subtract. Something like that. Okay. Now we get into what I think is a bit of a challenging piece. Find the equation of the parabola. And what I want to do is use an appropriate type of equation for a parabola, right? So normally when I think of a parabola, right, if I think of something like y equals x squared, we generally write it as something like y equals ax squared plus bx plus c. That's a general way to write the equation of a parabola, and that works great. That's fine for most applications. In this case, I want to take advantage of the information I have, and the information I have for this parabola is that I know it's x-intercepts, okay, and I have an extra point that we could take use of, make use of. But if I think about knowing the x-intercepts of a parabola, if I want to find the x-intercepts, right, you set it equal to 0 and solve, and you would solve this by factoring. So making use of the information I have, I want to start with the factored form of the parabola. I want to write this as, y equals a times x minus one intercept and x minus another intercept. Okay, and I still have a number out front because it can still be, stretched up or down, right? It's not, but this gives me a different way of writing the equation of a parabola, and this is the equation I want to use, right? The factored form. And so then I know the factors because I know what the x-intercepts are, right? This one is negative 5.90, the other one is 5.90. So my equation of a parabola is going to be some unknown constant a times x minus 5.9 times x plus 5.9. Okay, and if I wanted to, I could even, before I keep going, I could simplify this down a little bit because I know these are conjugates, so when I distribute, it'll simplify nicely. Right, x times x is x squared, then minus 5.9x plus 5.9x cancel, and then I get minus 5.9 squared. Which is 34.18. Okay. To find this value of a, I need an extra piece of information, and that's where I'm going to use this extra point. When you plug in 0 for x, you'll get 6.65 for y. Okay, so 6.65 equals negative 34.18a, and then I divide to get a by itself. So I have this negative 0.19104. Okay. So then the equation of my parabola is going to be y equals negative 0.19104 times x minus 34.18 squared. All right, that was a lot of work before we even see an integral. And now to find the area of the window, what I'm going to do is set up an integral. Okay, so the area is going to be the integral from x equals negative 5.9 to positive 5.9. And I just want the top curve minus the bottom curve. So I'm going to take the equation of the parabola minus the equation of the circle. Except the equation of the circle isn't a y equals equation. So I say, well, that's a little bit of a bummer. Can I write that as a y equals equation? Okay. So let's rewrite this equation of a circle. X squared plus y plus 12.25357 squared equals 184.96. I want to solve for y, so let's subtract the x squared. Okay, then I'm going to square root. I don't need the plus and minus here. I would if I wanted the entire circle, but it's okay to only get the equation for the top half of the circle because that's all I'm working with. So y is the square root of 184.56 minus x squared, and then outside of the square root, I subtract the 12.25357. Okay, so when I'm looking at area, my top function is the parabola, my bottom function is the circle. Okay, and I'd look at this and I'd be like, wow, is this a mess? How would I even integrate all of this business? Okay, and part of it just looks messy but isn't hard, and that's the parabola part, right? Because I could FOIL this out, and the decimal numbers make it a little messy, but that's okay. Over here, integrating the circle is actually going to be really difficult because I've got this x squared inside a square root. I'd say, oh, I don't know about that. That might be a little bit rough to work with. What we could do instead, because it's a circle, I know how to find the area of the whole circle, and then what I can do is I can just say, well, how do I find area of just one slice of a circle? Okay, so I could use a geometry formula instead of an integral here. So I could just integrate to get the area of the whole parabola. Okay, and then I could just subtract out whatever this area is and use geometry, just use a geometry formula for area of a slice of a circle like that instead of using an integral. An integral like this we will be able to integrate in the next chapter, but I think in this chapter I think we might be stuck there. Okay, so I think we're kind of stuck using a little piece of geometry. All right, any questions on this one? Okay, none of you asked this question anyway, so I think that we'll say that's good enough, and we'll call that it. Unless any of you have another homework question.